Okay, then I go on to the part where we talk about transformers. Let me just give you a brief idea of what does a transformer do. Now, the main function of a transformer is to step up or down voltages. That's the main function of a transformer. Now, how does a transformer actually work in the first place? If, say, for example, I have a transformer without iron core, say I have a transformer is just basically like this. You have an iron core and then you have a primary core here and then a secondary core here, right? So the core itself is actually a solenoid. It's a core with many turns. You can think of them as solenoid. Now, for the case of a transformer, if I talk to you about a case where it does not have any iron core yet, but they place close to each other, when you run current through your primary core, you know in your magnetic field chapter that when you run current through a solenoid, it's going to produce a magnetic field. And the magnetic field can be represented by your field lines or your magnetic flux. So here it could be a case where you have a magnetic field produced that looks like this. Then because this one is placed close to this, maybe you have it going somewhere like this. Okay. So here you see that there is actually some flux linkage from your primary core to your secondary core, but there's still some portion that doesn't link to your secondary core, right? So how do you make sure that you have more flux linkage with the secondary core? Here you see that in your case here, flux linkage with secondary core is minimum. There isn't a lot of flux linkage with the secondary core. So to make sure that you have more flux linkage with the secondary core, what you do is that you add an iron core. Now with an iron core added in like this, you still have your primary core, you still have your secondary core, but now you have this, you have your iron core here like this. Okay. Now the function of an iron core, we will tell you is something that they always test. They'll ask you what is the function of the iron core. We will say that the iron core, the purpose of the iron core is to improve flux linkage with secondary core, or we also say as to reduce flux loss or flux leakage. Okay, leakage, not linkage. So what we mean by that is that because you have an iron core here, it has the effect of redirecting the magnetic fluxes. So if originally just now you had this little flux that is already linking with secondary core, because you add an iron core here, this remaining two flux will join back to here. Okay, this remaining two fluxes will now join back to here. So that's why we say that it is called improving flux linkage or to reduce flux loss or flux leakage. That's the purpose of your iron core here now. Okay, so how is it that your iron core is able to have voltages? Okay, how does it induce a voltage inside your secondary core? How does it induce a voltage inside your secondary core? Now, remember I told you guys before that for solenoid, magnetic flux density is mu naught In. So B is proportional to I. Okay, this part is okay. Then when you talk about say flux linkage, you know that flux linkage is N phi, or in other words is NBA. So from here you can see that B is actually proportional to flux linkage. You have this relation here and you have this relation here. Now you add these two together, you're gonna get this. I is actually proportional to flux linkage. Okay, so you get this. Now your case here is that you want an alternating current to run through your primary coil. When you have an alternating current running through your primary coil, the relation you can see is this. If I were to draw for you a graph of, say, current versus time, this one would be how it looks like. This one is, say, in the primary coil, just revert this. This one is current in primary coil. Okay. Now the current in primary coil is what causes your flux linkage in your secondary coil. Okay, because your current flows, you get magnetic flux. Your magnetic flux is linking to your secondary coil, so you have flux linkage here. How does your flux linkage vary with time? You see that because your current is proportional to flux linkage, directly proportional to flux linkage, the graph of flux linkage versus time is going to follow exactly the shape of current versus time. Okay, so this is the graph of, say, flux linkage versus time for your transformer, sorry, for your secondary coil. This is the graph of flux linkage versus time for your transformer in the secondary coil. Okay, now then after that we will tell you this. You see your flux linkage is changing with time, and you know that EMF is defined as rate of change of flux linkage. EMF is defined as rate of change of flux linkage. It is actually the gradient of your flux linkage time graph. It's actually the gradient of your flux linkage time graph. So here you see that you have flux linkage change with time. You're definitely gonna have EMF induced. So how is your EMF induced gonna look like? So if we say that your EMF is the gradient of your flux linkage versus time, you just need to look at your gradients here. There are a few points of interest here. There's this point, there's this point, there's this point, there's this point, this point, as well as this point, right? So first thing first, I identify where is gradient 0. 0 gradient here, 0 gradient here, 0 gradient here. So this one is 0, this one is 0, this one is 0. And then after that, I see where is gradient maximum. Gradient will be maximum at this point here. Okay, this is maximum gradient positive, so maximum EMF positive. Maximum gradient negative, so maximum gradient is maximum EMF negative. So maximum gradient positive, maximum EMF positive, maximum gradient negative, so maximum EMF negative. So once you trace, once you have seen all the points, plot out all the points, you cannot plot out the shape. Oh, sorry, this part here shouldn't be here. This part here should be here. Okay, my mistake. So you go and plot out the points, you see that the points will describe to you this graph. Okay, so you see here, this is the EMF induced, but in your secondary coil. Okay, so when you have a variation of current or variation of voltage in your primary coil, it will tend to cause this kind of variation. Okay, it will cause your flux linkage in your secondary coil to change, and then in turn you will get an EMF induced in your secondary coil that looks like this. Now there's one question that you may sometimes encounter. They ask you to explain why is it that your EMF induced inside a secondary coil is not in phase with your primary coil? Why isn't it following exactly the same shape as your current? You see here, this one is a is a sine graph. This one is the cos graph. So you see they're not in phase, right? So the reason why they're not in phase is because of how EMF is defined in the first place. It's because it is the rate of change of flux linkage. You are actually looking at the gradient for the variation to get out the actual value of EMF. So you never get it in phase. If anything, you see that this one and this one is actually 90 degrees out of phase. Okay. Wait, let me do this. This is 90 degrees out of phase. Okay. So this is the graph of variation of EMF with time. And this is how you end up with a voltage in your secondary coil when you run alternating current through your primary coil. So we say that your transformer is used to step up and down voltage, meaning to say if you give a certain voltage here in the primary coil, you're gonna get another different voltage in your secondary coil. That one is your secondary coil voltage. So how are they related to each other? You need to know this relation. Your voltage in your secondary coil over the voltage in primary coil is equals to the ratio of the number of turns in your secondary coil to primary coil. Okay, this part is what you guys may have learned in IGCSE. In A2, we will add another set here for you where we tell you that in terms of current, this one will be current in primary coil to current in secondary coil. You will get this. Okay, how do you get this in the first place is from this. Now, if we say for you ideal transformer, there is no energy loss. That will mean for you that P powers in the primary coil, which is P in, will be the same as the power in the secondary coil, which is your P out. Okay, your P in here is your power inside your primary coil here. Your P out here is the power in your secondary coil here. If we say for you that your transformer is ideal, that means there's no energy loss. No energy loss means that P in is equals to P out. Now, if we have this relation here, you know that P is actually VI, right? So power in input is talking about power in the primary coil. It will be voltage of primary coil, current in primary coil. P out is the power in the secondary coil. So it will be voltage of secondary coil and current in secondary coil. So if you rearrange this again, you see that you can actually get this out, where you say that VP, sorry, not VP, you say that VS over VP is actually IP over IS, which allows you to tie it back to here. Okay, this is how we got this part in the first place. Okay, so this one is under the assumption that your transformer is ideal. But your transformer is actually not ideal in real life cases. You actually have power losses. So what are the sources of power loss? This one you can actually see from your notes. Your source of power loss for a transformer. The first power loss in your transformer could be through your coil resistance. I'm referring to page 5 of your notes. The first power loss in your transformer is your coil resistance. Now your transformer, they are made of wires, right? You have your primary coil and your secondary coil. These coils are made using wires. So your wire itself has resistance. When you run current through your wire, the wire will dissipate heat. The current flowing through the wire will dissipate heat. So this one causes your power loss. Hence, we say one of the first sources of energy loss in your transformer is actually called resistance, the resistance of your wire. And then the second power loss inside your transformer is actually losses due to eddy currents. Now, eddy current is normally formed within the iron core because your iron core is also experiencing a change in magnetic flux. Why do we say that? Is because if you just look back at this little diagram here, your iron core is here, the green object here with the green line here. You know that the purpose of your iron core is to improve flux linkage with secondary core, to reduce flux loss and flux leakage. So you see, when I have the iron core here, it has the effect of redirecting the magnetic flux so that it links to the secondary core. But at the same time, your magnetic flux is also passing through your iron core, as you can see here. Now, you know that your current is the one that is producing your magnetic flux. If you look back at this relation here, B is proportional to I, B is proportional to flux linkage. You can also say one thing, right? B is also proportional to flux. Wait, let me, yeah, no, I don't use from here. I just use from here, sorry. In the first place, I say that from this relation here and this relation here, I got this relation, right? I is proportional to flux linkage. I can also say that I is proportional to flux. Okay, so the thing here is that my magnetic flux here is also going to keep changing. The magnetic flux that passes through my iron core is also going to keep changing along with the current because the relation is I is proportional to flux. So if I want to talk about the variation of flux with time for the iron core, it will now look like this. Also sinusoidal. This one is magnetic flux versus time in iron core. Okay, it varies according to your current. So here you see that I also have change of flux with time, and EMF is actually rate of change of flux also, right? So it's actually the gradient of your flux time graph. So here you know you're going to have induced EMF also inside your iron core because your magnetic flux is changing. Your iron core will now have induced EMF. So the thing is that when you have induced EMF, you have induced current. So this part here, I can say that there is induced EMF, hence induced current. Okay, so I have induced current inside my iron core, but you see the induced current inside my iron core cannot go anywhere. It cannot flow into the primary core, it cannot flow into the secondary core because they are all electrically insulated from each other. The wires here have plastic covering around them, like the wires that you normally see inside your lab. If you go and coil it around an iron core, they are not making electrical contact whatsoever. So here, your iron core has current, induced current, but it will not flow to primary core, it will not flow in secondary core. It will just keep flowing inside your iron core. And when it keeps flowing inside your iron core, it will cause heat. So it dissipates heat away. The energy for that heat dissipation actually comes from the power of your transformer itself. Okay, that's one source of power loss here. So here for iron core, we say there is induced EMF, hence there is induced current. Now, eddy current in itself, you will sometimes hear mention eddy current. What is eddy current? Eddy current is just simply this. Eddy current is just current that has no particular direction of flow and tends to dissipate heat only. Okay, you can think of eddy current as just another form of current that doesn't have anywhere to go. Okay, and it's mainly just dissipating heat. So in the case of your iron core here, you will always have eddy current. You have eddy currents being produced. So you have induced current being produced because the currents cannot go anywhere. It's eddy current. So it has nowhere to go. So as it flows around inside your iron core, it will cause you to lose heat. So you lose heat, you lose power. Okay. How do you go and reduce your eddy currents? What we will tell you is that you use lamination. I think in IGCSE you also learned this already. If you want to increase the efficiency of your transformer, you want to reduce power loss, you use lamination. So what does lamination actually do for you here? When you increase your lamination, let me just write it here. Now, with lamination, your R would increase. When your R increase, your current will drop. Power loss is actually I square R. So if your I is increasing, your power loss will therefore drop. Okay, so that's the reason why you want to reduce eddy currents here. If you have eddy currents being reduced, you would have lesser power loss. You also have less heating, I'll put it another way. So you have less heating, you will have less power loss. Okay, so that part is for eddy current. So you want to reduce it, you use lamination because you're increasing the resistance. Then you reduce eddy current. Okay, then the other part of another source of power loss is your magnetic flux linkage. Okay, for magnetic flux linkage, we're just telling you that some of the magnetic flux that is produced in your primary core does not link with your secondary core. That one is easily seen in this case here just now that I talked to you about. If we are an iron core, you could say that some of your magnetic flux is linking with your secondary core, but there's some others that are not linking. This is what we call as your flux loss. This is what we call as your flux loss or your flux linkage. So not all of them is linking with your secondary core. So how do you overcome? So if you don't have all your flux linking with your secondary core, this one represents a source of energy loss also. So you want to reduce this flux loss or flux leakage, you need to design your transformer better, change the design of the transformer, put an iron core so that you don't have as much flux leakage. All right. So that part is okay. And then after that, the last part is hysteresis. Another source of energy loss in your transformer is hysteresis. Now, over here in your notes, we define hysteresis as the reluctance of a material to undergo changes in magnetization. Okay, so here during each cycle of AC, the core reverses the polarity of its magnetization, which requires energy. So this one is your source of energy loss. This is minimized by careful choice of material. Okay, what is hysteresis here in the first place? I will just talk to you about this. This one I'll just write it at the top. At the top here. Now, hysteresis was defined as reluctance of material to undergo changes in magnetization. Let me just write this. To undergo changes in magnetization. Changes in magnetization here is actually talking about changes in polarity of your magnet. Now, if I were just to talk to you about this portion here of your transformer, you see just now I told you that your primary core and secondary core here are just solenoids. They are actually coils with many turns. Now, if I ask you to just look at this part here, if I just cut off this part here, you'll notice that this part is just akin to a solenoid with an iron core inside. Alright. Now recall that last year I told you what's the effect of inserting an iron core inside a solenoid. You see, if I have a solenoid like this, and I tell you that current is going in, and then I produce a magnetic field like this. If I were to insert an iron core with iron core inserted, what will happen to this solenoid pattern is this. Your existing magnetic field will strengthen, right? If this was the original magnetic field, the moment you insert an iron core here, represented by, say, your blue lines here, the moment I insert an iron core here, what this will do is that it will increase the magnetic flux, right, represented by the additional blue lines here, isn't it? So why is this even happening in the first place? Why is it that your iron core is helping you to increase your magnetic flux? Now you see here, if I have this solenoid with no iron core inserted, I have current flow, I have a magnetic field produced, I would have a magnetic field with a certain direction, a certain polarity. It could be that maybe my magnetic field direction is B here, so that this one is N, this one is S. For example, once I insert an iron core, the iron core becomes magnetized. Okay, it becomes magnetized. It becomes a magnet in itself. Okay, so it becomes magnetized, it becomes a magnet in itself. Its magnetic field will add up to your existing magnetic field. That's the reason why your magnetic field will strengthen, and then you suddenly have increase in magnetic flux. But you see, when your iron core becomes magnetized, it becomes a magnet in itself. It will also have its own magnetic polarity. If originally your direction of magnetic field was, I think I use a separate color. What color? If originally the direction of magnetic field was here, such that this one is N, this one was S, when your iron core becomes magnetized, this one will also, the iron core itself will have a magnetic polarity of N and then S here. Okay, following your existing magnetic field. But say now you consider a case for alternating current. If for alternating current, you know that your current direction will continuously change. If in this case here, your current is now flowing from here to here, at the next instant, at the next cycle, your current may now flow from here and here. So if your current is now flowing in opposite direction, your magnetic polarity would change. Your magnetic field direction will change, your magnetic polarity will change. This one now becomes N, this one now becomes S, right? So if you have an iron core inserted, like in your case here like this, where if my current direction is changed, if I have an iron core that is inserted here like this, it also needs to change polarity. If now this one I tell you becomes N, this one now becomes S, the iron core itself, once you insert, it also needs to change its polarity. Okay, now the process of it changing its polarity when your current direction is changed requires energy. So the energy must be taken from somewhere. So in your case, the energy is taken from your transformer. Okay, so hence we define hysteresis as this. It's the reluctance of your material to undergo changes in magnetization or changes in polarity. If it is very reluctant to undergo changes in magnetization, you need a lot of energy to change the magnetic polarity. Hence, you have more energy loss. That is what hysteresis actually is. Okay, so to minimize this, use careful choice of material. Okay, so that part is okay. Then after that, we go on to the last part. I'll just stop right before rectification. I need to talk about the transmission of electrical power here. So if this one is okay, wait a minute, did I just close or something? Okay, so now this one is okay already. So let me just save this. Then I go on to your transmission of electrical power. Let me just close or something. Okay, now transmission of your electrical power. When we want to transmit electricity, we have the tendency to step out the voltages. Okay, now why do we want to step out voltages? You see, for example, right now, if this one was your power plant where you generate your electricity, you run your electricity through a transformer, you tend to step out your voltage before transmitting it to somewhere else. Okay, so why do we want to step out the voltage in the first place? The reasoning is because we want to reduce power loss. Okay, when we want to transmit electrical power, we tend to step up the voltage in the first place. Because if you recall the equation for transformer, which is SNP VS VP IS, sorry, IPIS. Specifically, if you look at this portion here, if voltage is secondary coil is increased, in other words, step up, your current in secondary coil would drop. So current in secondary coil drops will lead to less power losses in your transmission cables, because you can say that power loss here is actually I squared R. So if your I is dropping, your power loss should be dropping. So the thing here is this. This one is another different simplified diagram. If I want to simplify this whole thing, it will look like this. Okay, I think it's better you look at the diagram at the bottom here. So what we'll have here is that your transformer is here. Okay, your secondary coil is here. You step out the voltage, then your voltage, once you step out, your current will be reduced. So you transmit it to your home, and then after that, the current comes back to the power plant. It follows a closed loop like this. So here, when your voltage is step out, your current is reduced. Your current is reduced, your power loss is reduced. Okay, so that's the reason why we tend to step out your voltages, right? Because we want to reduce power loss. Okay, you ask why do we want to step out voltages before transmission? It's because we want to reduce the current flowing through your transmission cables. Once you reduce the current in your transmission cables, you have less power loss. Okay, so this part should be fine. So here what is actually happening here is this. Let me just use you step out your voltage, your current will flow like this. It goes to your load, then it comes back here to your transformer. If I want to draw a similar circuit here for you, it looks something like this now. It will look something similar to this. This is your wire. This is your wire. This is your transformer. And then this is your load, the ones in your house. Okay, so the current is going like this. If you increase your voltage here, your current here will drop. Okay, so this is transformer. Okay, transformers part, page 2 we done already. Maybe page 14. Okay, 14 seems to be with 16. I think we better do 16 first. Okay, right. 16 seems to be an easy one to do first before I increase the difficulty. Have a look at page 16.
Okay.
16. They ask you, they're telling you there's an ideal transformer there, but let me first see what question here is this. This is March 17 P42. March 17 P42. Question 9. Okay, so question 9, we have this one. Okay, so we have a transformer here. Explain to us why we want to make an iron core, why the core is made out of iron. Why do we use an iron core? Why is the core made of iron in the first place? So I mentioned to you in the last lesson that the iron core is meant to somehow strengthen the magnetic flux or to redirect the magnetic flux of your primary core so that links with your secondary core, right? I mean, without the iron core, that time I drew for you, it would just look like this, right?
Yep.
But then with your iron core, it has the effect of redirecting and strengthening your magnetic field such that it now looks like this. So that it links with your secondary core. Okay. So if you say that the iron is made of iron in order to increase the magnetic field strength, although that is true, but that's not the real reason why we use an iron core here. The main thing we want is that we want to link the magnetic flux from your primary core to your secondary core.
Yep.
So the answer is supposed to say, you're supposed to say to improve flux linkage with the secondary core. That is actually the main purpose of your iron core. You want to link the magnetic flux from primary core to secondary core. You want to improve the flux linkage with the secondary core. That's the main reason why you actually use the iron core. Right? And along the way, you increase the magnetic field strength. That is just a side effect of that, but that's not the main reason why you use iron in the first place. Okay, so to improve flux linkage with secondary core, sometimes they will also give you another variation of the answer where they say to reduce flux loss. Okay, flux loss is referring to the magnetic flux that did not link to your secondary core. I think that one, if you remember, I mentioned to you what are the sources of power loss in the transformer. I mentioned to you that there could be some cases where your magnetic flux is linking with your secondary core, but then there's some flux at the edge that may not really link with your secondary core. That is your flux leakage. Okay, that one is your source of power loss. So you use an iron core in order to cause this flux to link with your secondary core. You want to reduce your flux leakage. Okay? Reduce your flux loss now.
Yep.
Right? It's usually either one of these answers. Okay. Now, question 2. Why is it why an EMF is not induced at the output when the constant direct voltage is at the input? They are basically asking you, why is it that at the secondary core, you do not have an EMF when you're using direct voltage at the input? Simply put, if you're using direct voltage, it basically looks something like this. Now, if you use direct voltage, it's going to look like this. Now, voltage is related to current, so you can just think of it as variation of current with time also looks like this. Now, what can I also say about the variation of flux linkage with time then? You see, if I know that the magnetic flux in the primary core will actually link to the secondary core, if my current is constant in the first place, like this, my flux linkage will also be constant, right? With my secondary core here.
Yeah.
So we need our flux linkage to change in the first place in order to get an EMF, right? Because EMF is defined as rate of change of flux linkage. Remember?
Yep.
So if our flux linkage here is constant, we are never going to get any EMF, right? So we want to have EMF induced in the first place. So the only way we can get EMF induced is if your voltage is varying, your current is varying, such that your flux linkage is varying. So if you compare with this one, if I tell you your voltage, your current, your flux linkage is like this one you will have EMF induced. This one, no EMF induced. Okay, so this one, no EMF induced.
Okay.
Okay, this one EMF induced because there is rate of change of flux linkage. Okay, so that's the reason why you need alternating voltage in the first place. You cannot use direct voltage. So the answer will be something like this now. You will say that constant direct voltage produces constant magnetic flux. This flux actually links with the secondary coil, and EMF is induced only when flux in coil is changing. Okay, so if it doesn't change, you are not going to get EMF. So constant direct voltage produces constant magnetic flux. This flux links with the secondary coil. EMF is induced only when the flux in the coil is changing. Okay. Right, so this one is okay. Then after that, look at part B. Part B tells you that you have an alternating voltage or peak value 150 volts. Here, bear in mind that they tell you peak value 150 volts is applied across 1200 turns of primary coil. The ratio in time tail of the EMF E induced across secondary coil is as shown. This is the EMF induced in secondary coil right now. Okay, so from there, they ask you to calculate the number of turns on the secondary coil. They want you to find out the number of turns on the secondary coil. So this one, you can actually use the equation that you have in your notes, where in the first place, I told you that when it comes to calculations involving transformer, it will be NSNP, VSVP, or IP, IS, right? So since you want the number of turns, you will be using this one, but what's the other pair that you will use? Your question already gave you voltages, so this is the other pair that you want to use. Okay, so it will be NS to NP, VS to VP. So your number of turns on a primary coil in the previous page was 1200. Your voltage is 52 to 150. Okay, now this one here, we understand it as voltage. This one is one thing I did not mention before. This is the voltage in your secondary coil to your primary coil. It can be either RMS or peak values, but do not mix them together. But do not mix them together. Okay, what I mean by that is this. If let's just say the top part you're using RMS, the bottom part must also be RMS. This one will be okay. If the top part you use peak value, and then the bottom part you also use peak value, this one is also going to be okay. But the problem will arise if let's just say one of it you use peak value, and then the other one you use RMS. This one will be wrong. And this is what I mean by if you want to use the voltages or current values, RMS or peak values will be fine, but you cannot mix them together.
Right.
If you use RMS, all must be RMS. If you use peak, all must be peak. If you, basically just that. You don't mix peak and RMS together. So in our case here, we are actually using peak values. Okay. You see your alternating voltage or peak value 150 volts is applied across the 1200 turns of the primary coil. This one here is your primary coil voltage. Then this one here in your graph is your secondary coil voltage. Your peak value is over here. This one is at 52. Okay. Primary coil one, the peak value is 150. So since this is peak value here, in this graph here, you also find peak value. You're going to get it as 52. All right. So eventually your answer will just be 416 turns, just like that. Okay.
Okay.
Right. Okay. Then after that, part 2. State one time when the magnetic flux linking the secondary coil is maximum. Okay. By looking at this one is telling you your EMF induced with time. They want you to find out the time where the magnetic flux linking the secondary coil is maximum. Okay, now this one here may seem a bit confusing in the first place, but let me just give you a simple analogy first. Now, this one relates to what you learned in AS physics before under the chapter of kinematics. Now, we know that acceleration is actually rate of change of velocity, right? Okay. So if I ask you, let's just say I tell you this, velocity is max when acceleration is 0. Does this make sense to you? Okay, put it this way. Because acceleration is rate of change of velocity, okay, acceleration is defined as rate of change of velocity.
Yep.
If your velocity change, that means your acceleration, you have acceleration, right? This one basically means that as long as there is velocity change,
there
is acceleration.
Yes.
Because that's how it's defined in the first place.
Yep.
So if you reach maximum speed, maximum velocity, is your velocity going to change anymore?
No.
Okay, no, right? So your velocity cannot change anymore. Your acceleration is 0. Okay, so let me just write another supporting statement here. V is max when A is 0. V cannot change anymore, therefore accelerate. And max speed when V is max, V cannot change anymore. Therefore, A is 0. Okay, so there's some analogy here that you can think of. If I say that my speed is maximum, that means that acceleration is 0 because of how acceleration is defined. It's defined as rate of change of velocity. If my velocity cannot change anymore because it has reached the maximum, acceleration would therefore be 0. So it's something similar here right now because we know that EMF is defined as rate of change of flux linkage. So I can tell you that flux linkage is max when EMF is 0. Okay, because this one here is EMF is rate of change of flux linkage. All right. So here you want to find out the time where the flux linking the secondary coil is maximum. You can just say that flux linkage is maximum when EMF is 0. Okay. If your EMF is 0, your flux cannot change anymore.
Yep.
Okay. When EMF is 0, flux cannot change anymore. Okay, so just find the time in which the flux, the EMF is 0. It will be 0, 7.5, 15, or 22.5. Just choose any one of those times.
Okay.
Okay, right. Okay, then after that, you have part C. Okay, right. So part C, just give me a while. Okay, now it's 3:10 p.m. I need to go and collect something from downstairs. Okay, now it's 3:10 p.m. We'll just take a short 10-minute break, okay, until 3:20 p.m. You can have a look at part C first, okay? Try to digest what it's saying. Then after that, I'll resume this with you, okay?
Okay.
In the meantime, you can also take a short break.
Mm-hmm.
All right? Okay, so just give me 10 minutes. All right.
All right.
For the last part, they tell you a resistor is connected between the output terminals of your secondary core. The mean power dissipated in the resistor is 1.2 watts. It may be assumed that the varying voltage across the resistor is equal to the varying EMF shown in figure 9.2. To give you an idea of what was happening here, this one was basically saying this. You have an alternating supply connected across your primary core like this. And then you also have your secondary core like this, which is now connected across a resistor. So not forgetting your iron core here. They tell you that the resistor a resistor is connected between the output terminals of your secondary core is referring to this resistor here, which is connected to your output of your secondary core. So the mean power dissipated in the resistor is 1.2 watts. Here they tell you the mean power. So it means to say that this one here has a mean power of 1.2 watts. Okay, then they tell you it may be assumed that the varying voltage across your resistor is equal to the varying EMF shown in the secondary core in figure 9.2. Okay, so they want you to calculate the resistance of the resistor itself. So here, you want to make use of any equation or power that has resistance inside because they give you the resistance, they want the resistance here. So if let's say you say P equals to VI, P is equals to I square R, P is V square over R. The one without resistance is this one. So the first one you don't use. You could either use second or third. But then after that, when you look at your graph, the graph that you were given is voltage. Yeah. So it doesn't have current. So you won't use current. You will use the third one. So here, what you can say is that mean power applied to AC is actually half of your max power. So it's half V naught square over R. We use V naught here because we can read out V naught directly from the graph over here. This one here, we can actually see the V naught as this one directly. So we use V naught square over R and then half it. That one will give us our mean power. Okay. So do that and you will get your resistance as 1127 ohm. Just like that. Okay.
Yep.
Okay, then after that, the last part here, they'll ask you on this figure here, sketch the variation with time or the power dissipated in the resistor for time 0 to 22 milliseconds. So they want now you to sketch the variation with time of the power dissipated now. Okay, so just now I did draw for you a little the variation of power with time. We know it's going to be a sine square graph. Okay, but we can actually still show it also if I try to do it another different way. See, power is V square over R. Voltage, the power is V square over R. Voltage when applied to AC is actually V naught sine omega t. So you square the entire term, divide by R. What you're going to get is that power at any time is just going to be the same as V naught square sine square omega t over R. Okay. So just now I showed it to you using V naught power is V over. Just now I showed you P is equals to VI in the notes. Then I got to the conclusion that the power is a sine square graph. Now I'm doing the same thing, but I'm using V square over R. You're still getting the same conclusion. It's a sine square graph. Okay. So it will be a sine square graph that looks like this. But there are a few things that you are interested to know. Namely, where is the max power? You will be interested to know where is the max power. And then also where is where, and then from there, how do you know what is this time? Okay, so these are two main things that you are interested in knowing. Okay, so in order for you to be able to complete the graph, so to find the peak of the graph, you need to find P max. This one should be quite straightforward because we know that mean power is 1.2 watts. Mean power is half of P max. P max is therefore twice of your mean power is going to be 2.4. So this one we know it as 2.4 watts. Okay, but then how do we then subsequently know where are these times here? What are these times here? Okay, so the easy way to see, okay, how do we know what are the times where the power is 0 and what are the times where your power is going to be maximum? Okay, so the easy one to do is to look at the same equation here. We know that our P is max when V is max. Our P is 0 when V is 0. So we can actually refer back to the graph in the previous page, which was V versus T. We know that the variation with time was like this. The variation of your voltage with time looks like this. So from there, we can actually start to guess where is our P max, where is our P0. If the graph shape looked like this just now, these portions here is where our P is 0. Okay, maybe I should just indicate properly. These portions here in orange, this is where P is 0 because B is 0 here. Okay, and then after that, this part here is where P is max because B is max. Okay, this also includes the one at the bottom. Okay? P is max because B is max. Right?
Okay.
So that's how we got the respective timing there. You see the timing there are all corresponding to your velocity 0 and peak voltages. Okay, right? So that's how you draw this graph. Okay, so is this okay? Then I can move on to the next one.
Yep.
Okay. So I did 16 already. So maybe I have to look at page 18. Okay, so next one probably we look at page 18. Okay, it's 1 or 2 pages away, it's 2 pages away. So it's June 17 P41. Question 9 again. Okay, now state why the transformer has an iron core rather than having no core. This one we've just done it just now. So I mentioned to you it improves magnetic flux linkage with secondary core, or it reduces loss of magnetic flux linkage.
Right.
Do one of the answers. Okay. So yeah, be very careful about the wordings that you use when talking about why your core is made of iron. Let's just say, for example, we say that the iron core reduces loss of flux linkage or reduces flux leakage. Maybe I just say this one. If you're talking about this one, this term here, reduces loss of magnetic flux linkage, this one can be replaced with a term called flux leakage. Okay, so here the keyword here was that you're saying that it reduces flux leakage or loss of magnetic flux linkage. The marking scheme say you should never ever use these terms, prevent flux leakage or stop flux leakage. The thing is that you can never really stop or prevent them. You can only minimize. So if you say prevent or stop, this one is wrong. So you must use reduce. Okay.
Okay.
Right. So that's just one thing to note. And then after that, you look at part 2. They ask you to explain why the iron core is laminated. Okay, so we went through this before in the last lesson. We mentioned that your iron core itself will produce its own induced current. The current will flow and dissipate off heat. So this causes your power loss. So we say that lamination here reduces the size of your eddy currents. You're reducing the currents in the core. So the heating of your core is reduced.
Okay.
Or you have less power loss. Okay. You laminate your core in order to reduce the eddy currents, in order to reduce the current, and then from there the heating of your core is reduced, you have less power loss. As simple as that.
Yeah.
Okay, and then for part B, you will notice it has some similarity with the question that we just did. They tell you that by reference to the action of a transformer, explain why input of a transformer is an AC, alternating voltage, rather than constant voltage. So you will notice that the answers have some similarity. That this one here is actually, well, which question is it that I just did? This one was actually the last question that we did under page 16. You see this one here under page 16, we say why is EMF not induced when you have direct voltage at the input, which is at the primary core. Here they're asking you something similar again. Why must the input to the transformer, which in this case means why is it that the input at the primary core must be an alternating voltage rather than a constant voltage? So you're basically trying to explain the same thing again. And alternating voltage gives rise to a changing magnetic flux in the core. This changing magnetic flux links to the secondary core, and EMF is induced in secondary core only when the flux linkage is changing. Okay, so this one is 3 marks. You actually did the same, you are also answering the same question in the previous example. But in that question, it was only worth 2 marks. Okay. So notice that in that question, there were actually 3 different sentences. Only the first and the third sentence was given a mark. The second sentence, the flux links with the secondary core, that one was not given any mark. Okay. But over here, you saying the same thing, the magnetic flux, the changing flux links to the secondary core, this is where your other mark came from. Okay. So if you want to memorize, it's usually these 3 standard answers. No? Alternating voltage gives rise to a changing magnetic flux in the core. The flux links to the secondary core, and EMF is induced in secondary core only when flux linkage is changing. Okay.
Yep.
This one is okay. Right, so this one is okay. Then after that, let me look at the other one. 22. Okay, have a look at page 22. This one kind of relates to what I mentioned earlier. Page 22, this one is going to be what year? Page 22. November 17, P41.
Yep.
Okay, November 17, P41. Yeah. Okay, November 17, P41, they tell you, this is page 22. You look at the question, they tell you the mean value of an alternating current is 0. Okay, they tell you that the mean value of an alternating current is 0. This one I I mentioned this to you already just now. If you have current versus time, that looks like this. Your I average is actually 0. Okay, so here they're actually referring to this. The mean value of an alternating current is 0, but why is it that heating will still occur when there's an alternating current in a resistor? Okay, just now the example I gave you was actually through a filament lamp, but this one here, they gave you the example as through a resistor. They're asking you right now, why is it that when you use an AC supply, your resistor still dissipates away heat energy, even though your average current is 0? Okay, so there is actually two different choices or answers that you can use. You can just say the power dissipated is actually I squared R. Power dissipated in the form of heating actually depends on I squared or current squared. I squared will always be positive regardless of direction of current. You can have negative current, but your power, it will still be, you can have negative current, but the current will eventually becomes positive, right? Once you square it, isn't it? Yeah, all right. So that's what you say. Well, power dissipated is P equals to I squared R. So I squared will always be positive regardless of the direction of your current. The negative will still become a positive. Okay, so that one is okay. All right, then for part B, they ask you, transmission of electrical energy is frequently achieved using alternating high voltages. So just why do we use high voltages? Okay, this one is related to what I mentioned to you for transformers. Why is it that we usually step out of voltage when we want to transmit electricity? So if I refer back to the equation for transformer, you get something like this, right? So if your voltage in the secondary coil is step out, the current in your secondary coil is lower, right? So then after that, I also mentioned that power loss is I squared R. If your current drops, your power loss would also drop. Okay. So what we'll say is something like this. No? For same power transmission, a higher voltage has lower current. As current is lower, there's power loss in transmission cable. Since P is equals to I squared R. All right.
Okay.
So that one is okay. So why do we step out the voltages? Because less current, less power loss. And then the last thing we want to know is why do we need to use alternating voltages in the first place when we want to transmit power? It's because your transformers only work with alternating because you see, why do we need to use alternating voltages is number one, transformers only work with alternating current, right? Or alternating voltage now if you want to.
Yeah.
You want to make the statement a bit consistent. Transformers only work with alternating voltage. Then from there, voltage can be stepped up or down easily. Okay.
Yep.
Right. So this one is the two answers there. You can also say that voltage can be stepped up and down easily by transformer. Transformers only work with alternating voltage. No? Also can. It depends on how you want to write it. Okay. Okay, so this one is okay. Okay, then this one is all right. Then after that, this one is 35, page 35 just now. Okay, next one that we can do is, I think page 3. Page 3 we just done. Sorry, let me just load the question. 22 we've done. Okay. 14 we've done, I think. Okay, so let's just have a look at page 14. Okay.
Yep.
So number 16 P42. Number 16 P42. State Faraday's law, electromagnetic induction. I think now we can skip. We already know what it is. So this one is okay. Magnitude of induced EMF is directly proportional to rate of change of flux cutting or rate of change of flux linkage. So this one no issue. Okay, now part B. Part B is the one that we need to be careful about. Okay, now they tell you an alternating current is passed through an A-core solenoid. An iron core is inserted into the solenoid and then held stationary within the solenoid. The current in the solenoid is now smaller. Explain why the root mean square value of the current in the solenoid is reduced as a result of inserting the core. Okay, so let's have a look at this question here. So they say alternating current is passed through an air core solenoid. The iron core is inserted into the solenoid and held stationary. Why the IMS value of current in solenoid is reduced as a result of inserting the iron core? Okay, so you have solenoid connected to an AC. So what it looks like right now is something like this. If you have an solenoid, it looks like this right now. You connect it to an alternating power supply. Yeah, another thing I think I should probably mention to you, when you see something like this, two dots, and then when you look at circuits, circuit diagram, when you see two dots, like this, and then that the two dots is connected to some electrical component, this is your DC supply. Okay, but when you see the same two dots, which is connected to some other electrical component, but you have something like a wavy sign here, this one is talking about AC supply. Okay, so in case you're wondering, right? So when you see this symbol here, this one is talking about AC supply. Right now, they're telling you that your alternating current is connected to an AC, your alternating current or AC supply is connected to an A-core solenoid. Okay, so this one is your AC supply. It is giving you an alternating current that currently looks like this. This is a graph of I versus T. So they're asking you, why is it that right now, when if I were to insert a iron core into the solenoid and then hold it stationary, the current in the solenoid is now smaller. Explain why the root mean square value of the current in the solenoid is reduced as a result of inserting the core. Okay, so this one here would have slightly to do with what you've done in EM induction. Okay, so when current is running through my AC supply, when current is flowing out from my AC supply through the solenoid and going back, I know that I'm going to have a magnetic field being produced. Okay, but this magnetic field, does it remain constant before I insert the iron core?
Yes, it remains constant before you insert the iron core.
Okay, all right. Do you remember us mentioning before that current is proportional to flux is proportional to, sorry, current is proportional to flux density is proportional to flux or proportional to flux linkage, right? Any one of these relation, right? Okay, so can I say that my current here is constant right now? Looking at this,
No.
it's not constant, right? So you see here, right now, my flux linkage here is not constant. It changes with current. Okay, so the variation of my flux linkage with time would actually follow the same variation as my current. Okay, the changes of flux linkage with time will follow the same variation as my current. Okay.
Oh, okay.
Right. So you can think of this one as the current from your supply. All right. Now, because my solenoid is experiencing changes in flux linkage, we know that you have induced EMF, right? Correct. So I could have an I have induced EMF, I have induced current. According to Lenz's law, the induced current will try to oppose the flux change that causes it, right? So right now, I have an induced current given by this green colored line here that will oppose the current from my supply, okay? Because I do not want the current to increase anymore, right? If I have current increasing even more right now, I would actually have an even larger change in flux linkage. I would actually have an even larger induced current. But Lenz's law tells you you will try to prevent that from happening. So here, my induced current will try to oppose my supply current. So that one, so far, so good?
Yep.
All right.
Okay.
So this one, you're okay with that for now. You see this question here, we actually did it somewhere before. I believe we did it under page. Which page? I think it was under page. Yeah, we actually did something similar before under page 2. Okay, somewhat similar question, but there are some slight variations. Okay, so that time we asked you why is it that you have an EMF that opposes EMF for the battery when you insert the iron core, right? Something about once you insert the iron core, the flux linkage increases. You're going to have induced EMF, induced current. The induced current opposes the battery's current. The induced EMF opposes the battery's EMF, right?
Yep.
Right. So something similar is again happening here.
Okay.
All right.
Okay.
We are having a changing current. We are having changing flux linkage. We are going to have induced current, and it opposes the supply current. So from here, this is what is just happening without the iron core being inserted. Okay, we haven't gotten to the part where we tell you iron core is inserted yet. Right? So when you insert iron core, let's just say I insert the iron core right now inside. We know that the iron core will increase the magnetic flux. It strengthens the magnetic field, right? Okay. So here, what we'll say here is that if before this, if you look at this diagram over here, this one was a graph of flux linkage versus time before iron core was inserted. Okay, this one was before iron core was inserted. And we know the flux linkage will change with time following this variation. The moment I go and insert an iron core, because it has a tendency to strengthen the magnetic field, it's going to cause my flux linkage to become even larger in a manner similar to this. This one is after iron core is inserted. All right. Okay, so you look at this one. Since this one is telling me, when you look at this one, after the iron core is inserted, what can I say about my changing the rate of change of flux linkage? Is my rate of change of flux linkage going to increase or decrease? You see the graph is now longer now.
Yeah.
Once I inserted my iron core. what it will tell you is that the rate of change of flux linkage increases.
Yep.
Therefore, EMF induced or current induced increases. Okay, right? So because now I have a larger current, induced current, my induced current is increasing. I have a larger induced current opposing my supply current. So therefore, my root mean square value of current will be reduced. Okay? Whatever I just explained over here was just basically trying to tell you that you currently have an induced current opposing your supply current. But the question is asking you right now, why is it that once I insert an iron core, my root mean square value, or rather my current, suddenly decreases? All right. In the first place, my current is already reduced without the iron core. But why is it that when I go and insert the iron core, my current is reduced even more? It's because my iron core causes an even larger rate of change of flux linkage. I have a larger induced EMF or induced current opposing my original supply current or voltage. Therefore, my root mean square value will decrease. Okay, so you look at the answer now, probably it will make more sense to you once you read it sentence by sentence. The iron core produces larger rates of change of flux linkage. This statement here, larger rates of change of flux linkage, is actually related to this pink line here. Okay, so we will say that the induced EMF in the solenoid is now greater than before. This induced EMF opposes the applied EMF in the solenoid. Therefore, my current is smaller. My RMS current is smaller. Okay.
Okay.
Right, so this one is okay. Now, then you look at C. They tell you that practical transformers are very efficient. However, there are power losses in your transformers. State two sources of power loss in the transformer. There are a few things you can say. You can say that it is due to heating. You can say that your power loss is number one, heating due to eddy currents in your core. Okay, this one is talking about your transformers right now.
Yep.
They're asking you to identify the source of your power loss. The first one is heating due to eddy currents in your core. The second one is heating due to current flowing through the resistance of your cores. Okay, so this two is the most common one. All right. The third one, which is less common, is actually just you mentioning hysteresis losses or losses due to changing magnetic field in the core. But this one I mentioned to you is actually a very rare answer that most people don't really bother to use, but your marketing team does accept it. Okay, that time I mentioned to you, I did not explain this one because it's not so important. It will be easier for you to remember the first two. Okay, heating due to eddy currents, heating due to current flowing through the resistance of the core. Okay, so this one is okay. Then after that, there's another one, two questions. Wait, this one, number two, I've done. Okay, number one, I think the next one is one, page one. Okay, right, so I'll clear everything off. Okay, if you just look at page one, June 15, P41, question 7. Okay, so here they tell you that in many distribution systems for electrical energy, energy is transmitted using alternating current at high voltages. When you want to transmit electrical energy, you tend to transmit them using alternating current at very high voltages. Basically, you step them out before transmitting, you step out the voltage before transmitting them. So they're asking you to suggest and explain an advantage, one in each case, for the use of alternating voltages. and high voltages. Okay, why do why is it that you want to use alternating voltages in the first place? So this one is 2 marks. So we would say that we use alternating voltages so that your voltage can be changed efficiently by using transformers to suit different consumers or appliances. We use alternating voltages so that we can step up and down voltages. Okay.
Yep. Okay.
Using a transformer. And why do we want to do this? Is because we want to suit different consumers or appliances. Now this one here actually is a bit similar to what you did in the last 2 page. And this one here, we actually did something similar just now. Why high voltage are used? Why voltage is alternating? This one we say voltage can be stepped up and down. Voltage transformers only work with alternating voltages, right? So here you notice that the answers are somewhat similar. You use this a common answer. We want to step up and down voltages. Voltage can be changed efficiently. And why do we want to do that? It's because we want to suit different consumers and appliances. Okay.
Okay.
Right. Okay. Why do we want to use high voltages in the first place? So what we'll say here is that for the same power transmitted, current is smaller. Why do we use high voltages here is basically asking you why do we want to step up the voltage in the first place? For same power, current is smaller. When current is smaller, there's less heating in the cables, hence less power loss. All right.
Okay.
Okay, so this one is okay.